Hello and welcome to Chemistry with Dr. T. I'm Dr. T and today I will be presenting a short lesson on the Henderson-Hasselbalch equation. So what is the Henderson-Hasselbalch equation? It is an equation that is used to quickly calculate the pH of a buffer solution. A buffer solution is a solution that contains a weak conjugate acid-base pair that is able to accommodate the addition of strong acids and bases without the pH of the solution changing much. It is based on some underlying assumptions that I'll get to later in the video, and its main advantage is that the concentrations of the buffer components can be used directly in the equation rather than having to use an ICE chart. However, I always recommend that you write the chemical equilibrium equation to make the problems easier to solve. The derivation is found in your textbook or class lectures. So, what is it used for? As I mentioned before, the Henderson-Hasselbalch equation is used to quickly calculate the pH of a buffer solution. In the real world, biologists, biochemists, and chemists all use the equation to calculate the pH of various buffers for various experiments. Students also use the Henderson-Hasselbalch equation to calculate the pH of buffer solutions for laboratory experiments as well as homework and exam problems. The Henderson-Hasselbalch equation is shown in the bottom here. It states that the pH of a buffer solution is equal to the pKa of the conjugate acid plus the log of the concentration of the conjugate base divided by the concentration of the conjugate acid. So how is it used? I give an example problem here that 0.20 moles of benzoic acid and 0.10 moles of its conjugate base, sodium benzoate, are dissolved in 1 liter of pure water. What is the pH of this buffer solution? Given is the Ka of benzoic acid, which is 6.3 times 10 to the minus 5. This is normally found in your textbook or some other reference source. So, how do we use the Henderson-Hasselbalch equation? Well, first, as I mentioned before, I always recommend that you go ahead and write the chemical equilibrium equation first. So we'll represent the acid with HA, and this is in equilibrium with H plus and A minus, the conjugate base. These are all aqueous, of course. And what this shows is that a small amount of this weak acid in solution will dissociate into H+, which gives the acidity of the solution, and its conjugate base, A-. So we'll just write an I line of the ICE chart. And you start with 0.20 moles of benzoic acid in 1 liter of pure water, so that calculates conveniently to 0.20 molar. You start with 0 H plus and 0.10 molar in the conjugate base, sodium benzoate. So from here, we need the pKa. I gave you the Ka, but this is easily calculated in much the same way that the pH is calculated. The pKa is equal to the negative log of the Ka. And using 6.3 times 10 to the minus 5 here, we get that the pKa is equal to 4.202. Now, from here, we just plug our numbers into the equation. So pH is equal to the pKa, 4.202, plus the log of the concentration of the conjugate base, which is 0.10 molar. We get this from the I of the ICE chart. And this will be divided by 0.20 molar. The molars cancel out. And what this brings us to is pH is equal to 4.202 plus negative 0.301, and this will give us a final answer of pH is equal to 3.901, which rounds to 3.9. and that is it. That is how simple the Henderson-Hasselbalch equation makes it to calculate the pH of a buffer solution. Now I'd like to run through a few pieces of information that will help you understand the Henderson-Hasselbalch equation better, as well as to use it the most effectively. So the central assumption made by the Henderson-Hasselbalch equation is that the amount of acid that ionizes in solution is negligible compared to the amount of acid and conjugate base that are used to form the buffer. So what does this mean for you? This means that the Henderson-Hasselbalch equation is inappropriate to calculate the pH of a solution containing only a strong acid or strong base. For that, you would use that the pH is equal to the negative log of the concentration of H+ in solution. So you need to be sure that the amount of acid and conjugate base that are added are at least about 100 times larger than the Ka. So in our case, the Ka was 6.3 times 10 to the minus 5. So that means that you would want to add at least about 10 to the minus 3 moles of the conjugate acid-base pair in order for the assumption made by the Henderson-Hasselbalch equation to not be violated. I'd also like to tell you a little bit about pH and buffer capacity. The pH of a buffer solution is determined solely by the Ka of the conjugate acid. The amount of acid or base that can be added, the amount of strong acid or strong base that can be added to the system and neutralized by the buffer before the pH starts to change by a significant amount depends on the amount of conjugate acid and conjugate base used to make the buffer. This is known as the buffer capacity. So, for example, a solution that is 1 molar in benzoic acid and 1 molar in sodium benzoate will have the same pH as a solution that contains 0.1 molar in benzoic acid and 0.1 molar in sodium benzoate. However, the 1 molar solution has a much larger buffer capacity, and it can therefore neutralize a much greater amount of added strong acid or strong base. And with that, I would like to thank you for watching this short lesson on the Henderson-Hasselbalch equation. For more resources, please visit my website, www.chemistrywithdrt.com. That's chemistrywithdrt.com. Thank you.